So hello everyone, I'm Norman Wahlberger, and we're in this course in differential geometry. We're continuing on from this topic from last time, talking about curvature, turning numbers, degree and winding numbers. So the context is that we're sort of moving from thinking about curves algebraically to thinking about them parametrically. So instead of just thinking of a curve as an object like this, we think of it as the path traced out by a moving point or particle. So we usually have some kind of direction to our curve. And so that means that we can talk about the curvature in a little bit more directed way, so that we can talk about positive or negative curvature. So at some point here, if we look at the center of curvature, it might be over here, but at some other point over here we have center of curvature which might be over on this side. And so here we're moving in this direction. A small change d theta results in a ds, which is r times d theta. And same thing over here, but now the theta that we're really talking about has to be interpreted a little bit differently. So the best thing to do is to think about a tangent that's following our curve, or a normal that's following a curve. And there's sort of these 2 points of view. And last time we talked about the normal. So if we look at the normal to the curve, then there's something different happening at this portion. In this portion, the normal is moving in this direction, in the part A, while in this part here, it's actually going in the reverse direction. Okay. And so we had this formula that the total change in the angle theta formed by the tangent or by the normal can be obtained by integrating the small changes. So ds is equal to r d theta. That means d theta is equal to 1 over r ds. And we found this formula, integral of k ds, over the part of the curve that we're interested in. Maybe I'll write change in theta. So in particular, if we have a closed loop that goes around positively like this, then we expect that the total curvature for this curve gamma will be the integral of k ds over all of gamma, and that's going to be 2 pi, because the normal goes all the way around in its direction, perhaps forwards and backwards, but ultimately by the time we get back to where we started, the normal has gone once around, so for a total change in the angle of 2 pi. And more generally, we can talk now about the turning number of a curve, turning number of a more general curve, say tau of gamma equals, well, it's still given by the same formula, k ds, but now this is the total number of times that the tangent goes around, or the normal goes around, with an orientation, either positive or negative. So for example, if we have a curve that goes like this, we saw last time that we could compute this turning number by choosing a particular direction, let's say north, and seeing how many times or in what positions the normal is in that direction. So if we follow the curve around, then it's going to have another such normal direction right there. And then another, wait a minute, we have to choose the right side, so it's on this side here. Okay, so I think there's no other place where it's almost getting there, but then it doubles back like this and comes back like that. So in this case, there's only two places where the normal is in that particular direction, and in both of them, we're crossing in the right to left direction, which is kind of the positive direction, because it corresponds to going once around in this direction, which we denote positive. All right, so here we could just by looking at the positions of these places where the normal vector is pointing north and seeing which way the curve is moving through those normal positions, we can determine that the total winding number is 2. And it can be any integer. Okay, so this is a kind of an interesting property of a curve. Let's note that the turning number is not invariant under continuous transformations. Because we can continuously, if we want to, take one of these little loops, and we could, if we wanted to, deform such a little loop. Say if we just looked at that part of the curve, we could deform it continuously so that it becomes a smaller loop. And then eventually it just sort of stops there and goes like this, and eventually we could actually make it go. So we just need to be aware that continuous transformations can change things, and in particular, turning number is sensitive to having lots of little knots. If there's a little small knot or a little loop somewhere that's infinitesimally small, very small, then it's going to contribute to the turning number, but we're not going to be able to even see it. All right, so let's have a problem that allows us to connect these things explicitly with the curvature of some classical curve. So let's calculate the curvature and the evolute of the ellipse x squared over a squared plus y squared over b squared equals 1. So first of all, using a rational parameterization, where x equals a c of t and y equals b s of t, where c of t is 1 minus t squared over 1 plus t squared, and s of t is 2t over 1 plus t squared. These are the coordinates involved in the standard parameterization for the unit circle, and so they can be just dilated to give a rational parameterization of an ellipse. Okay, and so we can use that rational parameterization to calculate the curvature and the evolute, and then calculate, and the second part is without any parameterization. And the third part is calculate the total curvature, or verify that the total curvature is indeed 2 pi, like it ought to be. All right, so the idea of a turning number is a little bit like somebody on a roller coaster. You're on a roller coaster, and you are, while you're sitting on this roller coaster, you're moving, but you're also rotating around with respect to the environment. So if you're sort of looking at the scenery while you're going, you're seeing things sort of go by, and you're going around, and you say, oh, there's that tower again, now I see it again, and now I see it again as we're going around. So the turning number is really how many times you, as somebody on the roller coaster, there you are, going that way, how many times you turn around with respect to the environment, the fixed landscape. But there's another natural notion of turning that we might assign to a roller coaster, somebody on a roller coaster, and that's the different notion called a winding number. And the winding number is what we get when we look at this roller coaster from a fixed position, not on the roller coaster. So with what we're doing there is we're imagining an observer who's at some position, say P, and the point, say X, or let's call it gamma of T, on the curve is being viewed by an observer at a point P. And what we're interested in is how many times does that observer have to turn around to watch you on the roller coaster. All right, so at this position here, the vector joining P to the point on the curve, there's gamma of T, is in this direction. And as we're moving around, maybe I'll get a pen to illustrate. So as the point on the curve moves, okay, we're following it. It's not really done very much so far. And now it's gone around once. And now we're still following it. It still hasn't not much doing much, and it's still back to where it started. So overall, the viewer has had to turn around once at that position to follow the path of the person on the roller coaster. So we'll say that in this case, the winding number of the curve gamma with respect to the point P, okay, is, in this case, what do we say? 1. So it's the number of times that P must turn around to follow gamma of T as it goes around over one complete loop.
P can be any arbitrary quantity.
Yeah, so P is allowed to be arbitrary here. So we can fully expect, and we should expect, that this winding number is going to change if we change the point P. And let's see what would happen, say, if we chose that point Q there. Well, let's do a more interesting one where it's sort of more in the middle. Let's say this Q here. All right. All right, let's see what would happen. So there is our viewing vector to the point, and as we're moving around here, let's see what happens. Not much yet, and now we're over here. And by the time we're up here, it's gone around once. And then here, it's gone around twice. And then I think it's gone around 3 times, if I was counting correctly. So the winding number of the same curve, gamma with respect to q equals 3. Okay, so as a problem, check carefully for, say, this curve. So try to create it reasonably accurately. Obviously, it doesn't matter if you distort it a little bit. It's just the relationships of the loops with each other that matters. So check carefully for this curve what these values, and compute them for all the regions. Right? At least in principle, it's possible that the winding number is going to be different as we go from one region to another. All right, so we want to check carefully for this curve, these values, and compute them for all the regions. And that's kind of a natural question is there a pattern, or is there a way to predict, instead of having to do them one by one, what the various possibilities are? Is there any kind of pattern? And you might like to think about whether there is an algorithm that's similar to the algorithm that we used for the turning numbers to sort of efficiently calculate a winding number. I think you'll find that that's pretty easy to come up with. So in this context of winding number, there's a pleasant and almost amusing little theorem that's quite important in complex analysis that has to do with winding numbers. It's sometimes called the dog on a leash theorem or lemma. Okay, and it's in its simplest version, it's this: that you're taking your dog for a walk, and you're walking around a tree. We'll do it in green. All right, so here is a tree. And you are taking your dog on this walk, and it's going around the tree in a circle. And let's say that circle is a fixed circle of radius r. So you're walking along here. And you have a dog, which is on a leash. And the leash okay, at the end of it there is a dog. And what we're told is that if the length of the leash is less than the radius of this circle, then the winding number of the person with respect to the tree equals the winding number of the dog with respect to the tree. After they've both done one complete loop. After both return to the starting position. Okay, it's kind of obvious, but it's an interesting little fact that I think was perhaps introduced first by Poincaré in context of complex analysis, and does have a valuable role, where generally winding numbers can play a very important role in the theory of complex integration. How many times a curve goes around a point is a crucial kind of question when you're integrating certain functions around that curve. And there's singularities inside the curve. And you want to know, does this curve go around that singularity? And if so, how many times? So it's a very natural, important question. Okay, another application, sort of a special case of these considerations, is the discussion of the degree of a function or a map let's say phi, from the circle to the circle. Okay, so S1 here is just a circle, which you can think of as the unit circle if you like. So maybe it's the unit circle parameterized, say, by theta, the usual way. All right, as you're going once around the circle, you've got this function phi, and you're mapping to another, or perhaps the same circle, it doesn't matter. So the image of the circle over here is going to be some curve that starts and ends in the same place over here. So what we do is we look at the image as we go around here once. Well, the image is going to be something that wanders around the circle, and it can do rather arbitrary things. And eventually it will come back to where it starts. So any continuous map or function from the circle to the circle has a sort of a picture, something like this. As you go around here from 0 to 2 pi, the image is going to wander around the circle in some fashion or another, depending on the function. And so then we can think about this curve here as a curve in the plane that's going around the origin. And we can define the degree of this function or mapping to be the winding number of the curve, well, maybe gamma of t equals phi of t. The winding number of the curve gamma of t around the point O. So no, the image, well, I've drawn it like this, but the image actually has to lie on that circle. Okay, so I'm just showing you where it's going, but it's actually on the circle, going back and forth on the circle. Might go around lots of different times, and eventually it gets back to where it started.
So if you have less than the radius, the distance between the center point and the curve have to be less than the radius of the surface.
No, so the image of, this is a function from the circle to the circle. So every point on here goes to a point on that circle. Let's say it's a circle of radius 1 also, to be precise. Yeah. So every point here will go to a point on the circle. So if this is the point t, that would be the point phi of t. All right, so this is the notion of a degree, and it's an integer. And clearly, because it's a winding number, and it's an important sort of invariant of a function from a circle to a circle. Okay, so now I want to talk about parametric curves. In 2D and in 3D. Okay, so this is motivated by mechanics and the 17th century revolution in mechanics and calculus, initiated by Newton, essentially, that rests on Newton's famous law, F equals ma, for the motion of a particle of mass m, which is moving along and experiencing some acceleration. So it's really a vector equation. It's often written like this, but we probably should think of it for us as a vector equation, where the acceleration and the force are both vector quantities in the plane, perhaps, or perhaps in three-dimensional space. So this is a basic driving formula for mechanics, because it tells us that if we know the forces, then we know the acceleration, and then if we know how to integrate, with some luck, we can calculate the velocity and then the position. So that's the basic strategy. Okay, so it's motivated a lot of interest in dynamics of curves, and so we're going to sort of talk a little bit about curves in a parametric form. So maybe we'll work in the plane first. So a curve for us will be something of the form r of t is x of t and y of t. These are just two functions of t. And then we're going to define r prime of t is d by dt of r of t. And that's the derivative in each component separately. So it's x prime of t, y prime of t. And if this is usually called the position of, say, a particle, then this is, of course, the velocity. And then one more derivative. Maybe we call that v of t. That's going to be x double prime of t, y double prime of t. That's the acceleration. All right, so it's important to have a little bit of a physical understanding of the meaning of these things. So we're talking about vector quantities here. So if our particle, say, is right here at a particular point, say r of t, we're talking about a vector that's joining the origin, say, to the point in question. That's the basic vector that controls the position, and it's changing with respect to time. So as this vector is moving, as t goes along, the vector is moving, and there is a change in the vector. Okay, and that change in the vector divided by the change in time has a limiting value, and that's the velocity, which is going to be a tangent vector to the curve. Where's my red? Okay, so we're going to get a tangent vector. The way we can think about the velocity, r prime of t, is as a tangent vector to the curve. And of course, the size of that tangent vector is going to depend on its speed, which we should define as well. So the speed at any point is just the absolute value of the velocity. And because this is a vector, we have to take square roots, okay? So it's the size of r prime of t, so that's the square root of x prime of t squared plus y prime of t squared. And that will be the length of this vector. It doesn't have to be constant length. It can speed up and slow down as well. And then the acceleration is the change of these velocities. And so, for example, right at this point here, the velocity is going from a position here to a position here. And we have to remember that even though we're putting these vectors at various points on the curve, they're actually vectors, so that they're translation invariant. So that these two vectors that we've drawn here, let me call them v1 and v2, could really also be thought of here. So there is v1, we could translate that, and there would be v2, translating both to a common origin or common base. In that case, the change, v2 minus v1, is, well, you're going from here to here, so the change in the velocity is really measured rather in this diagram rather than directly here. So we should think of this as being the change in velocity. Change in the velocity. And then if we divide that by t and look at some limiting value, then we get an acceleration. Okay. So what we're finding is that the acceleration vector is going to be pointing in roughly this vector. An acceleration will have some direction like this. So there's an interpretation of what a of t might look like for this particular curve at that particular point. While over here, we would expect the acceleration to be in a different direction, because now the vector is going from this position to this position, so it's moving like this. And so the acceleration is more in a direction like that. And Newton's law is telling us that the acceleration is the force that you'd have to exert on this particle to make it go in this particular path. And clearly, if you want a particle to kind of bend this way a little bit, you have to pull on it in this direction right here. And then if you want it to turn around this way, you're going to have to pull on it in this direction a little while later. All right? So these accelerations that we're computing here are just the forces that this particle must feel if it's going to go in this particular path. That's what Newton's law is telling us. Okay, so let's have a look at some important example. So example 1, perhaps somewhat boring, but we could start with r of t equals some initial vector v, say v0, plus t times some vector w. Okay, so what is this? So here's some vector v0, and here's some vector w. Okay, and we probably should think of them as being vectors like this. So this motion, of course, is just a linear motion. It's what happens when you start at v0 and you add multiples of w. So you're heading off in the direction of w. And maybe you come from some previous time. So here would be time t equals 0. Here with time t equals 1. And t equals minus 1, perhaps. The particle is moving in this straight line through v0 in the direction of w. This is constant motion, which is the simplest motion, and this is constant motion. And we can find its velocity simply enough. V of t is just r prime of t. We can just do this differentiation because there's only a t dependence there, so the derivative is just w, which means that the velocity at every point is the vector w. So if we wanted to draw the velocity vectors, well, I guess they'd be w at any point, the velocity is w. That's a picture of the velocity vector at a time t on the curve. And then, of course, the acceleration is the derivative of the velocity, which in this case is 0. And so this corresponds to Newton's law of motion. This is what happens to a particle that has no force on it. Of course, these days this is quite obvious to us, but back in Newton's day it was a little bit of a revelation, because people thought that if a particle didn't have a force on it, it would slow down and stop, because that's what happens in real life. If there's no force on something, then it just slows down due to friction and eventually stops. But Newton's saying no force means it's actually going to keep on going. All right, so another simple but important example is a circular, or maybe harmonic, well, we'll just write, it's a circular motion, but of a uniform kind. So we'll have a circle of radius r, and well, we can parameterize this circle in a number of ways, but conveniently for us, if we want uniform motion, we might parameterize it like this. I'll say alpha of t, I can do it here, alpha of t equals, so it's radius r, so I'll use r cos theta, comma r sine theta. Oh, it's actually theta, all right, so okay, let me put t instead. T is actually theta, but we're thinking of these motions as being with respect to time usually, so it's nice to have t. All right, so that after time t, then there's the position alpha of t. It's exactly the same as the angle. So here we have these transcendental functions, cosine of t and sine of t, which of course we're just viewing approximately. Okay? And what are the definitions of cosine and sine? Cosine of x, let's say, is by definition 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so on. And sine x is by definition x minus x cubed on 3 factorial plus x to the 5th on 5 factorial minus x to the 7th on 7 factorial and so on. All right, so we're thinking about these things as power series, or as Newton would have thought, as infinite polynomials. And this allows Newton to think about things, algebra with objects like this, very much in the same way as you do algebra with polynomials, except that there's not a final term. One should perhaps remark that these formulas, which are the Taylor formulas for cosine and sine, were in essence known before Newton. Newton was the first European to have discovered them. But Newton's way of discovering them was actually roundabout. So just a small aside here. So if you have a circle, let's say a unit circle, for simplicity, then what we're talking about here is, say, let's say you have x, and then you have some angle theta. Okay, so we all know radius 1 circle, the relationship between x and theta is that x equals cosine theta. But in fact, it's probably a little bit more natural to think about the relationship going the other way around. In other words, if you hadn't been trained in this subject, you'd probably think the natural question is, given an x, what is the angle? That's a more natural question than asking, given an angle, what is the x? So the inverse function is really more natural geometrically, is the inverse function, which is arc cosine of x, which is usually not as well remembered by undergraduates, and I have to always remind myself what it is. So it is pi over 2 minus, and there's essentially, it's really pi over 2 minus arc sine of x. So what follows here is arc sine of x. That's x plus 1/2 x cubed over 3 plus 1 times 3 over 2 times 4 x, all of that, times x to the 5 over 5, and so on. And Newton, in fact, Newton discovered this formula first, because the natural question is, given x, how do you find a formula for theta? And you can work it out somehow or another and get this formula. But it turns out that this formula was in fact known before Newton by Indian mathematicians. So there's an Indian mathematician, Madhava, who I believe lived in the 14th century, maybe 15th century. And his school, maybe we're not entirely sure if he knew these formulas, but anyway, his school certainly knew this formula in Kerala, southern India, in the 16th century, so these were sort of well known. So basically the arc cosine, the arc sine, arc cosine functions. How did Newton go from here to here? He just inverted this formula. So if you have this equal to something else, let's say you set it equal to z, and then you ask yourself the question, all right, how can I solve for x in terms of z? We've sort of done something like that before. If you let x be an unknown power series in z with undetermined coefficients, you can plug it in, expand everything out, compare coefficients, and one by one you can find the various coefficients. And Newton would have been amazed that from this rather complicated formula, doing all this work inverting this formula, then miraculously you end up with this relatively simple and beautiful formula for the cosine and the sine. So it's quite opposite to what happens with the tan function, which is worth mentioning. So for the tan, things are a little bit opposite. So there the formula that's well known is the formula for tan itself. X minus, no, for arctan rather. Arctan of x equals x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. And then the formula for the tan now is the harder one. So inverting that, you would get x minus 1/3 x cubed plus 7 over 15 x to the 5th plus 17 over 315 x to the 7 plus 62 over 2835 x to the 9 plus so on, whatever so on means. Certainly not clear what the pattern is. In fact, it's not so easy to give a direct formula for the coefficients here for the tan-Taylor series. There's a recursive aspect and the sort of geometrical interpretation of the coefficients, but a direct formula of the nature of this we don't have. All right, so that's good. So we have a little bit of introduction to these circular functions, I like to call them, because they're really associated with the uniform motion on a circle. And so now let's have a look at this motion. All right, the uniform motion around the circle of radius r, given by alpha of t equals r cos t, r sine t. So carrying on with what we had over there, alpha prime of t, if we differentiate that with respect to t, what are we going to get? So the derivative minus r sine t and r cosine t. And so the speed, alpha prime of t, absolute value, is the square root of r squared sine squared plus r squared cos squared, so it's just r. And the acceleration is another derivative. We get minus r cosine t, r minus r sine t, which we recognize as being minus the original alpha of t, which is telling us simply that the acceleration is constant. This is constant acceleration, constant size acceleration, let's say. So corresponding to a central force field at the origin. So in this picture, we have, there is the vector alpha of t, the vector alpha prime of t, which is the derivative, would be just the thing rotated by quarter turn. So there is alpha prime of t. And then the acceleration in this direction, alpha double prime of t. Okay, so when we're studying curves and motion, it turns out that we can reparameterize things because our our coordinate t, in this case, is rather variable. So we can easily reparameterize a curve by replacing t, well, maybe with 2t or minus t or maybe some fancier function of t, as long as the function is sort of reasonable, sort of invertible. So that means there's a lot of flexibility in how we choose a parameterization. If we're just given a geometrical curve, there's no straight, immediately obvious parameterization to choose. There's many different possible parameterizations. So there's a kind of standard convention in the subject, which is to think about the simplest possible parameterization is to use, when possible, a unit speed parameterization. That means we're going to agree that we're going to try to go along the curve in such a way that at each point the velocity has exactly the same size, namely 1. So we want, let me write beta, let's say beta of s. We want beta prime of s, which is the size of the tangent vector, to always be 1. Yeah, it's a kind of a standard convention that we can adopt to make it simpler to talk about curves and give us some kind of anchoring point. So next time we're going to have a look at what the relationship between curvature and unit speed curves is. We're going to go to 3 dimensions, look at curves not just in the plane but in space, and introduce the Frenet-Serre formulas for the curvature and torsion of a curve going through 3-dimensional space. So more of these vector ideas, but now the vector ideas in 3 dimensions, and they're moving with the curve. So we'll see you then.